Far beyond the quiet glitter of the night sky, an object from another star system is behaving in ways that shouldn't be possible. 3I-ATLAS, once just a passing wanderer, has erupted after skimming the Sun, unleashing colossal jets that stretch nearly 3 million kilometres into the dark. Astronomers studying the latest November 9th, 2025 images are whispering the unthinkable. This isn't normal comet physics. Some, like Avi Loeb, warn it may have violently broken apart, or reacted as if under control. With its closest approach to Earth on December 19th, the world's telescopes are preparing for what could become the most consequential observation campaign of the decade. One that might show whether we've just witnessed a harmless disintegration, or the beginning of something far larger. Stay with me until the end, because if this is more than a harmless breakup, then it might be a warning, and what happens next could change everything we thought we knew about our place in the universe. If this mystery continues to have you hooked the way it has me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and what you think about this new development. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. The Nov 9 Shock. Jets. Too big for physics. On November 9th, 2025, astronomers around the world opened their morning data feeds and found something that shouldn't exist. The images were clear, undeniable, and profoundly unsettling. Comet 3I-ATLAS, the interstellar visitor that had been quietly approaching our Sun for months, was now ejecting material into space on a scale that defies every model we have for how comets behave. The jets stretching behind this object measured 2.8 to 3 million kilometres tailward. The jets pointing toward the Sun, defying the solar wind itself, reached nearly 1 million kilometres sunward. To put that in perspective, the distance between Earth and our Moon is roughly 384,000 kilometres. These jets are nearly 8 times that distance. They dwarf anything we've ever seen from a comet. You might be thinking, okay, so it's a really active comet. Comets do weird things sometimes, right? They outgas, they develop tails, they can be dramatic. But here's where the mathematics become a problem. According to calculations published by Harvard astrophysicist Avi Loeb, this object is losing mass at a rate of billions of tons per month. Some estimates put it at 50 billion tons monthly. For a normal comet to produce jets of this magnitude through simple sublimation, through ice turning to gas under the Sun's heat, it would need a surface area far larger than what we observe. The Hubble Space Telescope has given us size estimates for 3I-ATLAS. The numbers don't add up. The object we see is too small to be doing what it's doing through natural processes alone. This creates what scientists call an energy budget problem. Every physical system has to balance its books. Energy in must equal energy out, plus whatever gets stored or transformed. For 3I-ATLAS, the energy required to throw billions of tons of material millions of kilometres into space, month after month, exceeds what sunlight hitting its surface could reasonably provide. It's like watching a campfire consume an entire forest's worth of wood, but when you look closely, there's only a single log burning. The fuel source doesn't match the output. Now, we're not jumping to conclusions here. Science doesn't work that way. There could be exotic explanations within the realm of natural phenomena. Perhaps this object contains volatile materials we've never encountered before. Substances that release energy far more efficiently than water ice or carbon dioxide. Perhaps its interior is structured in ways that concentrate and channel outgassing through specific vents, creating collimated jets rather than diffuse clouds. Perhaps we're witnessing some kind of runaway thermal process, a positive feedback loop where initial heating triggers deeper layers to explosively decompress. All of these remain possibilities, but they're stretching possibilities, scenarios that require us to invoke conditions we've never observed in any comet, ever. And then there's the date that everyone's circling on their calendars, December 19th, 2025. On that day, 3I-ATLAS will make its closest approach to Earth at approximately 1.8 astronomical units. That's about 270 million kilometres, far too distant to pose any collision risk. But distance isn't the issue here. What matters is observation. December 19th represents our best opportunity to determine whether this object survived its close encounter with the Sun, which occurred on October 29th, or whether it shattered into fragments, or whether something else entirely happened. The verdict we get on December 19th will fundamentally shape how we interpret this visitor. There are essentially two broad categories of outcome. The first is catastrophic natural breakup. In this scenario, the intense thermal and gravitational stresses near the Sun tore the object apart. What we're seeing now is the death throes of a comet, a massive debris field expanding into space, jets formed from the violent liberation of trapped volatiles as the structure disintegrated. This would be spectacular, certainly unusual in scale, but ultimately explainable within our current understanding of physics. Nature gone wild, but still nature. The second possibility is something far stranger. If 3I-ATLAS arrives on December 19th intact, if it still shows a coherent nucleus with continuing jet activity, if it's still behaving as a unified object rather than a cloud of fragments, then we have to start asking very different questions. We have to ask whether this behaviour represents controlled propulsion. We have to ask whether we're looking at something that was designed rather than formed. We have to ask whether the jets aren't jets at all, but exhaust. Before we spiral into speculation, let me be clear about something. The default assumption in science is always natural explanation. Comets are strange. They surprise us. The universe is far more inventive than our imaginations. Every time we've encountered something anomalous in astronomy, from pulsars to fast radio bursts, the answer has eventually proven to be exotic physics, not extraterrestrial engineering. The odds heavily favour a natural explanation for 3I-ATLAS, even if that explanation involves comet behaviour we've never documented before. But odds aren't certainties, and the scientific method demands we remain open to wherever the evidence leads. So what's coming in this investigation? We're going to unpack the geometry of these jets, understanding why their structure and orientation matter. We're going to examine the composition of the material being ejected, looking for chemical signatures that might tell us about this object's origin and nature. We're going to compare 3I-ATLAS to previous interstellar visitors, seeing what patterns emerge and what stands apart. And we're going to explore both the natural and unnatural possibilities, laying out the logic chains without prejudgment. Because on December 19th, when the world's most powerful telescopes turn toward this visitor, we need to know what we're looking for and what it means if we find it. Part 2. Sunward and anti-sunward jets, structure, intent, or accident. Let's talk about something that keeps comet scientists awake at night: directionality. When you look at a typical comet, you see a relatively simple structure. There's a nucleus, the solid body at the centre. Around it forms a coma, a diffuse cloud of gas and dust. And streaming away from the sun, pushed by solar radiation pressure and the solar wind, you get the classic tail. Sometimes there are two tails, a dust tail and an ion tail, but both point generally away from the sun. This is Comets 101. This is what we expect. 3I-ATLAS doesn't follow this script. The images from November 9th show multiple distinct jets, not a simple diffuse coma. These jets are collimated, meaning they're narrow and focused rather than spreading out in all directions. Some point directly away from the sun, which makes sense, but others point toward the sun, fighting against the relentless outward pressure of solar radiation and the solar wind. This anti-sunward component shouldn't persist. It should be blown back, dispersed, overpowered by the forces pushing outward. Yet there it is, maintaining its coherence across nearly 1 million kilometers of space. To understand why this matters, we need to think about what creates jets in comets. Natural outgassing tends to form relatively broad fans or plumes as subsurface ice heats up and escapes through cracks or weak spots in the crust. You might get some directionality if the vents are concentrated on one side of the nucleus, particularly if the comet is rotating. You can get active regions that turn on and off as they face toward or away from the sun. But what you don't typically get is multiple highly collimated jets pointing in contradictory directions simultaneously. Compare this to Comet Eson, which disintegrated spectacularly as it grazed the sun in 2013. Eson showed jets, yes, but they were consistent with thermal stress and structural failure. Or look at Comet C 2023-A3, which put on a beautiful show recently. Its jets aligned with what we'd expect from rotating active regions. Even 2I/Borisov, the second confirmed interstellar comet that visited us in 2019, behaved like a normal comet, just one that happened to come from outside our solar system. 3I-ATLAS stands apart from all of these examples. There's a speculative thread here that we need to acknowledge, uncomfortable as it might be. If you wanted to design a propulsion system for a spacecraft travelling through the solar system, you might use jets of material expelled in specific directions to adjust your trajectory. Point jets one way, you thrust the other way. This is basic Newtonian physics, the same principle behind rocket engines. The jets we're seeing from 3I-ATLAS, particularly the anti-sunward component, would be consistent with active course correction or deceleration. I'm not saying that's what's happening, I'm saying the geometry permits that interpretation. The natural alternative involves assuming the object has a highly unusual internal structure. Perhaps it's fragmenting in a specific pattern, with cracks propagating along lines of weakness that happen to channel gas in these particular directions. Perhaps we're seeing explosive decompression from isolated pockets of supervolatiles, materials that were trapped under pressure and are now venting catastrophically through whatever paths they can find. Perhaps magnetic fields or electrostatic forces are shaping the jets in ways we don't fully understand. All of these mechanisms are theoretically possible, though none have been observed producing effects on this scale before. The rotation rate of the nucleus matters here too. If 3I-ATLAS is spinning rapidly, centrifugal forces could contribute to mass loss and might explain some of the observed jet patterns, but we don't have good data on rotation yet. The object was relatively faint until recently, and detailed photometry across enough time to establish a rotation period has been challenging. This is one of the things observers will be looking for on December 19th. Is there a periodic variation in brightness or jet activity that would indicate rotation? And if so, does that rotation pattern explain what we're seeing? There's also the question of timing. These jets didn't appear suddenly on November 9th. They've been building as the object approached and then passed perihelion, its closest point to the Sun on October 29th. The peak activity should have been around perihelion, when solar heating was at maximum. What we're seeing now, weeks later, represents continued activity well after that peak. For a normal comet, we'd expect activity to decline as it moves away from the Sun. The fact that 3I-ATLAS is maintaining or possibly increasing its output suggests either a very unusual thermal profile or an energy source that isn't purely solar. Here's where the geometry becomes truly puzzling. The solar wind, that stream of charged particles constantly flowing outward from the Sun, exerts pressure on any material in its path. For the sunward jets to persist against this pressure, the particles being ejected must have significant velocity. Typical comet outgassing produces speeds of around 400 meters per second. To punch through the solar wind and maintain coherence over 1 million kilometers would require velocities substantially higher than that, perhaps 10 to 50 kilometers per second. That's rocket exhaust velocity, not sublimation velocity. As we move forward in this investigation, we're going to dive deeper into the mass loss calculations, the composition of what's being ejected, and what those numbers tell us about energy budgets and possible mechanisms. Because the jet structure we're observing isn't just visually striking, it's physically demanding. It requires power, lots of it, delivered in specific ways through specific channels. Whether that power comes from exotic chemistry, catastrophic disintegration, or something else entirely, we need to know. December 19th is approaching fast, and with it answers. Part 3. The Loeb argument. Controlled, not comet. There's a scientist at Harvard who has made a career out of asking uncomfortable questions. His name is Avi Loeb, and he's the astronomer who suggested that 1I/Oumuamua, the first confirmed interstellar object to visit our solar system back in 2017, might have been artificial. He took tremendous heat for that suggestion from colleagues who felt he was sensationalizing limited data. But Loeb has maintained his position. When the evidence doesn't fit natural explanations comfortably, we have a scientific obligation to consider alternatives, no matter how unlikely they might seem. Now Loeb has turned his attention to 3I-ATLAS, and he's reaching similarly provocative conclusions. In a series of posts and analyses published on Medium, and in academic contexts, he's laid out a case that the object's behaviour is incompatible with our understanding of comet physics. The core of his argument rests on numbers, and numbers are hard to argue with. According to Loeb's calculations, 3I-ATLAS is losing mass at a rate of approximately 50 billion tonnes per month. That's not a typo. 50 billion tonnes. Every single month. To put that in perspective, consider what it means for an object to sustain that kind of mass loss. If the comet is sublimating, turning ice directly into gas through solar heating, then we can calculate how much surface area would be needed to produce that amount of outgassing. Ice sublimation is a well-understood process. We know how much energy it takes to vaporize water ice or carbon dioxide ice. We know how much solar energy hits a square metre of surface at different distances from the sun. The math is straightforward, and when Loeb runs those calculations, he finds that 3I-ATLAS would need to be 4 to 10 times larger in diameter than what Hubble observations indicate. This is what he means when he says, quote, "Houston, we have a problem. Either the object is much bigger than we think it is, hidden somehow behind dust or viewed from a misleading angle, or the mass loss isn't happening through normal sublimation. There's no comfortable middle ground here. The observational constraints from Hubble give us a size estimate. The jet activity gives us a mass loss estimate, and those two estimates are in fundamental conflict. The scientific community's response has been mixed. The majority of astrophysicists maintain that 3I-ATLAS is still most likely a comet, albeit an unusual one. They point out that our models are based on limited data from solar system comets, and we should expect surprises from interstellar objects that formed under very different conditions. Perhaps 3I-ATLAS is extraordinarily rich in supervolatiles like carbon monoxide or molecular nitrogen, which sublimate much more readily than water ice. Perhaps its internal structure is unusually porous, giving it a much larger effective surface area than its external dimensions suggest. Perhaps we're underestimating its true size due to observational limitations. All of these caveats are reasonable, but Loeb argues that invoking special circumstances every time an object doesn't fit our models is a form of intellectual complacency. At some point, the accumulation of anomalies demands a different framework. If the jets are effectively thrusters, if they're producing directed thrust rather than passive outgassing, then the energy budget problem becomes much more tractable. A propulsion system doesn't need to vaporize all of its reaction mass through solar heating. It can carry its own energy source, chemical, nuclear, or something more exotic. And a propulsion system can achieve much higher exhaust velocities than natural sublimation, which means less mass is required to produce the same momentum change. Let me walk through the logical structure here, because it's important to be precise. Start with what we observe. Object size from imaging, jet extent from photography, mass loss rate from spectroscopy and photometry. From these observations, we can derive the energy required to produce the observed effects. If that energy requirement exceeds what natural processes can plausibly provide given the object's size and distance from the Sun, we have three options. First, our observations are wrong. We're measuring the wrong values somehow. Second, our understanding of physics is incomplete. There's some natural mechanism we're not aware of. Third, the object is not entirely natural. It's been modified or constructed to behave this way. Loeb is careful to emphasize that the third option isn't proven and has a small probability attached to it. But he insists it's non-zero. The probability isn't so low that we can dismiss it without investigation. And if there's even a 1% chance that we're looking at an artificial object transiting through our solar system, doesn't that warrant serious attention? Doesn't that change the stakes of our observations? This is where things get philosophically interesting. Science operates on parsimony, the principle that we should favour the simplest explanation that fits the facts. Usually, that means favouring natural over artificial, accident over design. But parsimony assumes we have a good understanding of what's simple and what's complex in the relevant domain. If we don't actually know much about interstellar objects, if our sample size is 3 and they're all weird in different ways, then what's parsimonious? Is it simpler to invoke special physics we've never seen before, or to acknowledge that engineering is a thing that happens in the universe and might occasionally produce objects that travel between stars? The December 19th observation will be crucial for testing Loeb's hypothesis. If the object has broken apart, if we see a dispersed debris field with no coherent nucleus, then the case for artificial origin becomes much weaker. Breakup would suggest structural failure, which is hard to reconcile with designed engineering unless we're looking at something incredibly ancient and degraded. But if the object remains intact, if it still shows a well-defined nucleus with continuing jet activity, if there's any evidence of trajectory modification or non-gravitational acceleration beyond what pure outgassing would produce, then the questions Loeb is raising become impossible to ignore. We would have an object that looks like a comet, behaves like something else, and demands an explanation we're not currently prepared to give. Part 4. Catastrophic breakup versus silent survivor. Science loves binaries, clear either-or scenarios where observations can definitively rule one option in and the other out. Reality, of course, is rarely so accommodating. But with 3I-ATLAS, we're facing something close to a true binary. Either this object broke apart under the intense stress of its solar encounter, or it didn't. Fragmentation or survival. And each possibility tells a radically different story about what we're dealing with. Let's start with the breakup scenario, because it's the one most comet scientists expect. Comets are not solid monolithic rocks. They're better described as dirty snowballs or icy rubble piles, loose aggregations of ice and dust held together by their own weak gravity, and sometimes by organic compounds acting as a kind of tar. When a comet plunges close to the Sun, thermal stress is immense. The sunward side heats up dramatically while the shadow side remains frigid, creating temperature differentials that generate mechanical strain. Subsurface ice vaporizes faster than gas can escape, building pressure until something gives. Rotation creates centrifugal forces that pull the object apart. And if the comet passes close enough, the Sun's tidal gravity, the difference in gravitational pull between the near and far sides of the object, can literally rip it to pieces. We have examples of comets that didn't survive perihelion. Comet Ison, which I mentioned earlier, essentially evaporated during its 2013 encounter with the Sun. Comet Shoemaker-Levy 9 famously broke into more than 20 fragments before colliding with Jupiter in 1994, though that was tidal disruption by Jupiter rather than the Sun. The point is, cometary breakup is common, expected and well documented. Given the mass loss rates we're observing from 3I-ATLAS, given the extreme environment it passed through at perihelion, fragmentation would not be surprising. In fact, it might be the only way to explain the current level of activity within purely natural frameworks. Fragmentation models suggest that if 3I-ATLAS has indeed broken up, we should expect to see several characteristic signatures when we observe it on December 19th. First, multiple distinct nuclei rather than a single coherent body. These fragments would be separating from each other over time, creating an expanding debris field. Second, a diffuse, extended coma without well-defined structure. As fragments tumble and outgas independently, their individual jets would create a chaotic, overlapping pattern. Third, changes in total brightness that don't correlate simply with distance from Sun and Earth, because we'd be seeing different fragment cross-sections as they rotate and separate. Fourth, possible trajectory variations, because individual fragments would experience different levels of outgassing thrust and would drift onto slightly different orbits. If we see these signatures, case closed, right? It was an unusual comet that broke apart under stress. We learn something about the structural limits of interstellar objects. We track the debris. We maybe get some nice meteor showers in a few years when Earth's orbit intersects the fragment stream. It's good science, publishable results, but not paradigm shifting. Now consider the alternative. December 19th arrives. Telescopes focus on the expected position of 3I-ATLAS, and there it is. A single, compact nucleus. The jets are still there, still collimated, still defying simple expectations. Spectroscopy shows continuing activity at levels that shouldn't be sustainable for an object that size. Astrometry, precise position measurements, might even show slight deviations from the predicted orbit, deviations consistent with non-gravitational acceleration, with thrust. What then? Survival of an intact nucleus after this level of mass loss and energy expenditure would be profoundly weird. Remember Loeb's calculation. If the object has lost 16% or more of its original mass through natural processes, it should have either fragmented into at least 16 pieces, or it should be visibly smaller than it was before perihelion. A coherent survivor implies either that the mass loss estimates are wrong by an order of magnitude, unlikely given multiple independent observations, or that the object is vastly denser and more structurally robust than any comet we've studied, or that the jets aren't primarily mass loss at all but represent something else. Exhaust from an active system that's using fuel far more efficiently than thermal sublimation could. The phrase game over keeps appearing in discussions among astronomers tracking this object, though they mean different things by it. Some mean game over for Earth, we're about to be hit, but that's not the concern. The orbital geometry rules out impact for centuries to come regardless of what happens to the object. What they really mean is game over for our comfortable assumptions about comets and interstellar visitors. If 3I-ATLAS is still whole, still active, still behaving like something under control, then we've moved from the realm of unusual natural phenomena into territory where we genuinely don't have adequate explanations. There's also a middle ground possibility that's worth mentioning: partial fragmentation. Maybe the object has shed some outer layers, or split into 2 or 3 large pieces rather than completely disintegrating. This would be consistent with high mass loss, but wouldn't necessarily look like a chaotic debris field. It might appear as a nucleus with a companion object or two, each producing its own jets. This would be interesting scientifically, but wouldn't resolve the fundamental energy budget questions. We'd still be left asking where all that activity is coming from and why it continues so far from the Sun. The implications of survival extend beyond just the physics of this particular object. If 3I-ATLAS remains intact, we have to reconsider what we thought we knew about the strength and composition of interstellar bodies. We have to wonder whether there's a population of unusually robust objects out there in the galaxy, objects that can survive close stellar encounters that would destroy normal comets. And we have to confront the possibility that some fraction of interstellar visitors might not be random debris from planetary system formation, but something more deliberate, objects travelling between stars with purpose rather than by accident. December 19th is 10 days away as I record this. 10 days until we get our answer, or at least the beginning of an answer. The world's best telescopes are allocated, observation schedules are set, teams are ready. What they see will shape our understanding not just of 3I-ATLAS, but of our place in a galaxy that might be far more populated and active than we've dared to imagine. Part 5, the orbital wildcard, fragments and chaos. On paper, the orbital mechanics of 3I-ATLAS look reassuring. The comet reached perihelion on October 29, 2025, at a safe distance of about 0.7 astronomical units from the Sun, inside the orbit of Venus but nowhere near close enough to threaten Earth. Its closest approach to our planet comes on December 19th at approximately 1.8 AU, about 270 million kilometres away. That's more than 4 times the distance to Mars at its farthest. NASA's Centre for Near-Earth Object Studies lists 3I-ATLAS as no threat. Impact probability, 0. We can all sleep soundly, except there's a problem, and it's one that mission planners and satellite operators are starting to take seriously. Those reassuring calculations assume the object remains a single coherent body, following a predictable elliptical path. If 3I-ATLAS has fragmented, all bets are off. Breakup doesn't just create multiple objects, it creates multiple objects on perturbed trajectories, and the perturbations can be significant. Here's why fragmentation matters so much. When a comet breaks apart, each fragment carries away some of the parent body's momentum, but that momentum gets redistributed. Fragments spin off at different angles and velocities depending on how the breakup occurred. More importantly, each fragment then becomes subject to non-gravitational forces that affect it differently than the original body. Solar radiation pressure pushes on dust particles, and the smaller the particle, the more strongly it's pushed relative to its mass. Outgassing from individual fragments creates rocket effects, tiny thrusts that accumulate over time into measurable trajectory changes. And if any of the material becomes electrically charged, which happens readily in the solar wind, electromagnetic forces come into play as well. The result is a debris field that expands and evolves in ways that are fiendishly difficult to predict, without detailed tracking of every major fragment. Some pieces might end up on orbits that intersect Earth's path months or years from now. Others could threaten satellites in high Earth orbit or lunar infrastructure if we're unlucky. The risk isn't catastrophic collision with Earth, our atmosphere would handle most debris just fine, but rather more subtle hazards that come from having a cloud of high-velocity particles scattered across a region of space that we use regularly. Satellite operators are already concerned. There are thousands of active satellites in various orbits around Earth, from low Earth orbit constellations providing internet and communications to geostationary platforms, handling broadcast and weather monitoring. Add in space stations, both current and planned, plus the increasing activity around the Moon as multiple nations work on lunar programs. These assets represent trillions of dollars in infrastructure and irreplaceable scientific and practical capabilities. A micrometeoroid impact at orbital velocities can destroy a satellite. Even a particle the size of a grain of sand travelling at tens of kilometres per second hits with the energy of a hand grenade. Now multiply that threat by billions of particles if 3I-ATLAS truly shattered. Most of them would miss Earth entirely, spreading out along the object's orbital path. but the probabilistic risk increases dramatically when you're not tracking one object but a swarm. This is one reason why December 19th is so critical. We need to know whether we're dealing with an intact body, a few large fragments we can track, or a diffuse cloud that turns a region of interplanetary space into a navigation hazard. There's another concern that sounds like science fiction, but is grounded in real physics: geomagnetic disturbances. If the debris from 3I-ATLAS includes a significant charged particle component, either ionized gas from continued outgassing or electrically charged dust grains, then its interaction with Earth's magnetosphere could produce effects beyond simple collisions. The solar wind constantly pushes charged particles past Earth, and our magnetic field deflects most of them toward the poles, creating the aurora. But a dense, fast-moving charged cloud arriving from an unexpected direction could temporarily distort the magnetosphere, potentially affecting satellite electronics, radio communications, even power grids if the disturbance is severe enough. Is this likely? Probably not. Would it be unprecedented? Not quite. We've seen geomagnetic storms from coronal mass ejections that had similar effects, but a storm triggered by cometary debris would be novel, and novelty in space weather is rarely good news for infrastructure operators. This is why monitoring continues well past December 19th. Even if we determine the object's fate on that date, tracking the evolution of any debris field becomes a months-long or years-long project. The timeline matters here. If breakup occurred around perihelion on October 29th, we're now 3 weeks out. Fragments would have had time to separate by thousands or tens of thousands of kilometres, depending on their initial velocity differences and the forces acting on them. By December 19th, 7 weeks post-perihelion, that separation could be hundreds of thousands of kilometres. Fast forward 6 months, and you're potentially looking at a debris field spread across millions of kilometres of space, still loosely following the parent body's orbit but with enough dispersion that any single fragment could be anywhere within a broad swathe of possibilities. This is why professional astronomers are coordinating observation campaigns. It's not just about satisfying scientific curiosity, though that's certainly part of it. It's about getting actionable data that can inform decisions about spacecraft maneuvers, satellite operations, and mission planning for future years. If there's a dense debris cloud in a particular region of space, you want to know about it before you send anything valuable through that region. For the amateur observers and space enthusiasts following this story, there's a tendency to focus on the exotic possibilities, the artificial origins, the paradigm-shifting implications, and those are genuinely interesting questions worth exploring. But for the people whose jobs involve keeping satellites operational and humans in space safe, the immediate concern is much more prosaic. Where are the pieces? How many are there? And what's their trajectory? On December 19th, we begin to get answers. But the full picture might take months to resolve, as telescopes worldwide continue tracking, measuring, and refining orbit determinations for every detectable fragment of what was once Comet 3I-ATLAS. Part 6. The energy deficit. What could possibly power this? Every magic trick has a secret, and the secret is usually disappointingly mundane. The coin doesn't actually disappear, it's palmed or dropped through a hidden slot. The assistant isn't really sawn in half. There are 2 assistants and a carefully designed box. The whole art of stage magic relies on misdirection and engineering. So when we encounter something in nature that seems magical, that appears to violate our expectations, the scientific instinct is to look for the hidden mechanism, the mundane explanation we're missing. With 3I-ATLAS, we're looking for the mechanism behind impossible energy output. The object is doing something, generating jets that span millions of kilometres, expelling material at rates that stagger calculation. Energy is being released, work is being done in the physics sense, and that energy has to come from somewhere. It can't materialise out of nothing. Conservation of energy is one of the most fundamental principles in physics, violated only in quantum contexts that don't apply at comet scales. So where's the energy coming from? Let's work through the possibilities hierarchically, starting with the most conventional and moving toward the exotic. First, standard solar heating and sublimation. A comet's ice absorbs sunlight, heats up, and transitions directly from solid to gas, skipping the liquid phase because of low pressure. This is how normal comets work. For 3I-ATLAS, we can calculate exactly how much energy the Sun delivers to its surface based on its distance and size. That gives us a maximum theoretical energy budget. The problem is, the observed activity exceeds that budget by factors of several to 10, depending on whose estimates you trust. The magic trick isn't working with the energy source we can see. Second possibility, exotic volatile reservoirs. Maybe 3I-ATLAS isn't primarily water ice like most solar system comets. Maybe it's rich in carbon dioxide, carbon monoxide, nitrogen, or even more volatile substances like methane or ammonia. These materials sublimate at lower temperatures than water ice and can release more energy per unit mass. Spectroscopic observations show that carbon dioxide makes up an unusually high fraction of the gas around 3I-ATLAS, reportedly 87% in some measurements. That's far higher than typical comets, which are usually water-dominated. So yes, exotic volatiles are present, and they help explain some of the activity. But do they explain all of it? The calculations suggest not quite. We're getting closer to closing the energy gap, but we're not there yet. Third, thermal runaway scenarios. Imagine deep inside the comet there are pockets of volatile material that have been insulated from space by overlying layers. As the comet approaches the sun, heat slowly conducts inward. When it reaches these pockets, they vaporize rapidly, building pressure until they burst through to the surface in explosive events. Each explosion exposes more volatile-rich material, which then also vaporizes, creating a positive feedback loop. This could produce extremely energetic jets far beyond what steady-state sublimation would generate. The challenge is explaining how such pockets survive for the presumably millions of years this object has been travelling through interstellar space, and why they're all triggering now rather than having been exhausted long ago. Fourth, phase transition energy. Water ice comes in different crystalline forms, amorphous and crystalline, and the transition from amorphous to crystalline releases heat. Clathrate hydrates, where gas molecules are trapped in ice cages, can also release energy when they break down. If 3I-ATLAS contains large quantities of these materials in metastable states, their transformation could provide an internal energy source beyond solar heating alone. Again, this helps, but the question is whether it helps enough. The numbers remain challenging. Now we start getting into truly exotic territory. What if the object contains radioactive materials? Natural radioactive decay produces heat. It's what keeps Earth's interior molten billions of years after formation. Could a comet contain enough radiogenic material to matter? For a normal comet, no. The abundance of elements like uranium and thorium is far too low. But if 3I-ATLAS isn't a normal comet, if it formed in an unusual environment or has an unusual composition, maybe the rules are different. This is speculative, but not impossible. We'd need spectroscopic evidence of specific elements to confirm it, and so far we don't have that data publicly available. Here's where things get uncomfortable. If natural energy sources can't fully account for what we're observing, we're left with two options. Either our observations are wrong, which seems unlikely given multiple independent measurements, or the object contains an artificial energy source. By artificial, I mean deliberately engineered, whether by us, unlikely given the trajectory and timeline, or by someone else. The exhaust from any propulsion system capable of interstellar travel would necessarily involve high energy densities. Chemical rockets wouldn't cut it for star-to-star journeys. You'd need nuclear fission, nuclear fusion, antimatter, or something even more advanced. Avi Loeb has pointed out that if the jets represent high-velocity exhaust rather than simple sublimation, the mass loss requirements drop dramatically. Typical comet outgassing velocity is around 400 meters per second. Rocket exhaust velocity can be 10 to 50 kilometers per second, 100 times faster. Since momentum equals mass times velocity, achieving the same thrust with faster exhaust means you need 100 times less mass. Suddenly the energy budget starts to balance. Because you're not trying to vaporize 50 billion tons of ice per month, you're expelling a much smaller amount of fuel at much higher speeds. This doesn't prove anything. It's a consistency argument, showing that an artificial explanation is at least physically possible where natural explanations are strained. But possible doesn't mean actual. The history of astronomy is filled with anomalies that eventually found natural explanations. Pulsars were initially jokingly called LGMs, little green men, because their regular radio pulses seemed too precise to be natural. Turns out they're rotating neutron stars, exotic but entirely natural. Fast radio bursts, mysterious intense radio flashes from deep space, were once considered potential alien signals. They're now understood to be natural, if not entirely explained phenomena from cosmic sources. So where does that leave us with 3I-ATLAS? We have an object doing something that stretches our current models. We have several possible natural explanations that each get us part of the way there, but none that fully satisfy the observations without invoking special circumstances or unknown physics. And we have an unnatural explanation that fits the data, but requires accepting something we've never confirmed: technology of non-human origin actively operating in our solar system. The scientific method doesn't tell us to pick whichever explanation feels most comfortable. It tells us to follow the evidence, test predictions, and update our beliefs based on what we observe. December the 19th gives us a critical test. If the object has fragmented, if we see clear evidence of structural failure, then the artificial hypothesis becomes much harder to sustain. Designed objects don't usually break apart catastrophically unless they're very old or damaged. But if 3I-ATLAS remains intact, if it continues showing organised activity with high energy output, if there's any hint of trajectory control, then the energy deficit problem becomes acute. We'll need to answer not just what powers this, but who or what built it and why. The implications ripple outward from that question like shockwaves through water. If interstellar probes exist, how common are they? Have others passed through unnoticed because they were inactive or too small to detect? What's their purpose? Exploration, mapping, communication relay, something we can't imagine. And perhaps most unsettling, if someone else can send devices between stars, why haven't we heard from them directly? The silence becomes louder when you know someone's been watching. For now, we're left with an energy budget that doesn't balance using known natural mechanisms. That's not proof of anything except our ignorance. But it's the kind of ignorance that demands investigation, the kind that could either expand our understanding of astrophysics or confirm we're not alone in the galaxy. Both possibilities are worth the effort. Both change everything. Part 7. Composition Mysteries. The XO87 carbon signature. Chemistry is truth in a way that appearances are not. You can disguise an object's shape, hide its size behind dust, misjudge its distance and brightness. But when you break light down into its component wavelengths, when you read the spectral fingerprints of what atoms and molecules are present, you're getting direct information about material reality. Every element and compound absorbs and emits light at specific frequencies, determined by quantum mechanics. These signatures are universal, the same in our solar system as in galaxies billions of light years away. Spectroscopy doesn't lie. So when spectrographs pointed at 3I-ATLAS and analysed the light from its coma and jets, they revealed something odd. The gas surrounding this object is dominated by carbon dioxide, not water vapour. Depending on which measurements you look at, carbon dioxide makes up approximately 87% of the volatiles, with carbon monoxide and other species making up most of the rest. Water, the primary component of every comet we've studied up close in our solar system, is present but not dominant. This is unusual, not impossible, but unusual. Most comets are described as dirty snowballs because they're primarily water ice mixed with dust and smaller amounts of other frozen volatiles. When they heat up, water vapour is the main gas we detect. The famous comets, Halley, Hale-Bopp, all showed water-dominated compositions. Even 2I/Borisov, the previous interstellar comet, looked chemically similar to solar system comets. 3I-ATLAS stands apart. A carbon dioxide-rich composition tells us something about where and how this object formed. Water ice condenses from the protoplanetary disk at relatively warm temperatures compared to other volatiles. You find water-rich bodies in the region where giant planets form, roughly 3 to 30 astronomical units from a star. Carbon dioxide and carbon monoxide stay gaseous at those temperatures. They only freeze out much farther from the star, in the cold outer reaches of a planetary system or beyond. An object dominated by these supervolatiles suggests formation in an extremely cold environment, perhaps in the Oort cloud equivalent of another star system, or even in interstellar space itself. This fits with 3I-ATLAS being an interstellar visitor, at least on the surface. It came from somewhere cold, somewhere far from stellar warmth, and it preserved that primordial composition during its journey to our Sun. But the preservation itself raises questions. Interstellar space isn't empty. There's radiation, cosmic rays, the the ultraviolet glow from distant stars. Over millions or billions of years, these gradually erode and alter surface materials on any object not protected by an atmosphere or magnetic field. For 3I-ATLAS to still contain such large quantities of supervolatiles, it either hasn't been travelling very long, geologically speaking, or it has some kind of protective layer that prevented sublimation and radiation damage during the journey. One hypothesis involves a carbon-rich crust. Imagine the object formed with a surface layer of organic compounds, complex carbon-based molecules that created a dark, insulating shell around a volatile, rich interior. This shell would protect the ice from interstellar radiation and prevent sublimation in the cold of deep space. When the object approached our Sun and heated up, the shell would eventually crack or breach, allowing the pressurized interior volatiles to escape explosively. This could explain both the delayed onset of activity. 3I-ATLAS didn't show jets until relatively close to the Sun, and the intensity of that activity once it started. But there's a puzzle within the puzzle. If you have a protective crust that's doing its job, keeping volatiles locked inside, why would it breach in multiple locations simultaneously to create the multiple collimated jets we observe? Crusts crack along lines of weakness. Yes, but the pattern we're seeing seems organised. The jets are persistent, directional, and symmetrically arranged in ways that suggest structure rather than random failure. This is where speculation edges towards science fiction. Could the crust be more than just a passive protective layer? Could it have structure, channels, venting systems that control outgassing? In nature, we don't typically see this level of organisation. Comets don't have plumbing, but if we entertain the possibility of deliberate engineering, suddenly the composition makes sense in a different way. You'd want supervolatiles as fuel because they're energy-dense and easy to store in cold environments. You'd want a protective shell to prevent loss during the long journey, and you'd want controlled vents to direct thrust when and where needed. I want to be clear about the speculative status here. We have no direct evidence of artificial structures in 3I-ATLAS. The carbon-rich composition is unusual but not impossible for natural objects. The jet pattern is odd, but could potentially be explained by internal structural features like voids or fractures. We're in the territory of could be, rather than must be, and science demands we acknowledge that distinction. There's also the question of what we haven't detected. Spectroscopy reveals what's emitting or absorbing light strongly. If there are other materials present in smaller quantities, or if there are structures that don't interact strongly with light, we might miss them. This is particularly true for metals or other non-volatile materials. A normal comet's dust component includes silicates and sometimes iron compounds, but these are typically a small fraction of the total mass. If 3I-ATLAS has a different ratio, more metals or exotic materials, we'd need different observations to detect them. NASA and other space agencies have detailed spectroscopic data that hasn't been fully released to the public yet. There are mentions in the scientific community of high-resolution images and spectra that are still being analysed or are subject to classification review. This fuels speculation, sometimes justified, sometimes not, about what might be known but not shared. The reality is probably less conspiratorial. Data takes time to calibrate, analyse, and prepare for publication. Scientists want to be sure of their findings before announcing them, but the delay creates information gaps that speculation rushes to fill. What we can say with confidence is that 3I-ATLAS has a composition that's consistent with formation in a very cold environment and inconsistent with typical solar system comets. That alone makes it interesting. Whether that composition is purely natural, the result of formation in a different stellar system's outer reaches, or whether it reflects engineering choices made by designers, remains to be determined. The December 19th observations won't answer this directly. Composition doesn't change based on survival or fragmentation, but they'll give us context. A fragmented object would strongly suggest natural processes struggling with structural limits. An intact object would keep all possibilities on the table, including the ones that make us uncomfortable. Part 8. Comparisons to 1I, Oumuamua, Similar Echoes, Critical Differences. In October of 2017, a telescope in Hawaii detected something that should have been impossible, an object moving through our solar system on a hyperbolic trajectory, meaning it came from interstellar space and would leave again, not bound by the sun's gravity. They named it 1I/Oumuamua, Hawaiian for scout or messenger, and it immediately became one of the most scrutinized objects in astronomical history. For the first time, we had confirmation that stuff from other star systems could and did visit ours. The universe was more connected than we'd realised. Oumuamua was strange from the start. It was small, only a few hundred metres long, and elongated, maybe cigar-shaped, or possibly flat like a pancake. The data wasn't clear. It tumbled as it moved, rotating every 7 to 8 hours, and critically it showed no signs of cometary activity. No coma, no tail, no jets. To all appearances it was an asteroid, a rocky or metallic object rather than an icy one. But then something weird happened. As astronomers tracked Oumuamua's trajectory with high precision, they noticed it wasn't following a purely gravitational path. It was accelerating away from the Sun slightly, a tiny push beyond what gravity and orbital mechanics predicted. The acceleration was small, but definitely real, measurable across multiple observations. For a comet, this would be easily explained. Outgassing creates thrust, pushing the object as gas escapes. But Oumuamua showed no outgassing, no visible jets or coma, so where was the push coming from? Multiple hypotheses emerged. Maybe there was outgassing, just too faint to detect with our instruments. Maybe the object was venting pure hydrogen, which is nearly invisible. Maybe it was a fragment of a larger body, with unusual shape causing radiation pressure from sunlight to accelerate it differently than a spherical object would be. Or maybe, as Avi Loeb famously suggested, it was artificial. A light sail, a thin reflective sheet pushed by sunlight, exactly what humans have proposed for interstellar travel. The scientific community largely rejected the artificial hypothesis, not because it was impossible, but because it required extraordinary claims without extraordinary evidence. Occam's razor suggested invisible outgassing was more likely than alien probes, but the debate highlighted something important. We don't actually know what's normal for interstellar objects. Our sample size was 1, and that one was weird. Drawing conclusions about what's typical from a sample of 1 is statistically meaningless. 2 years later, in 2019, a second interstellar visitor arrived, 2I-Borisov. This one was unmistakably a comet. It had a bright coma, a classic tail, and chemical composition similar to solar system comets. It outgassed normally, followed predictable paths, and behaved exactly as our models expected. Borisov was almost boring in its normalcy, which was actually reassuring. It suggested that Oumuamua might have been an outlier, a statistical fluke, and that most interstellar objects would be recognizable as variants of things we already knew. Now we have 3I-ATLAS, and it's neither Oumuamua nor Borisov. It shows vigorous cometary activity, unlike Oumuamua, but that activity is so extreme and unusual that it challenges our models, unlike Borisov. It's as if 3I-ATLAS is synthesizing the strangeness of both previous visitors into a single package. The visible activity we expected from Borisov combined with the anomalous behaviour that made Oumuamua so perplexing. Let's compare specifics. Oumuamua. No visible coma, possible non-gravitational acceleration, unusual shape, rocky or metallic composition inferred. ATLAS. Massive coma and jets, likely non-gravitational effects from outgassing if not something else. Size and shape still uncertain, carbon dioxide-rich composition. Oumuamua was faint and hard to study. Observations were limited because we didn't know it was special until it was already leaving. ATLAS was detected earlier in its approach, giving us months of observations and the upcoming December 19th close approach for detailed study. The lesson from Oumuamua was clear. We need better detection systems and faster response protocols. The astronomical community has taken this to heart. Surveys like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, set to begin operations soon, will dramatically increase our detection rate for asteroids, comets and interstellar visitors. When the next Oumuamua comes through, we'll spot it sooner, track it better, and maybe even send a spacecraft to intercept it. But ATLAS presents a different challenge. It's not about detection, we saw it coming. It's about interpretation. We have data, lots of it, and that data is strange enough that multiple competing explanations can each claim some support. This is actually more difficult than the Oumuamua situation. With Oumuamua, we could say, we don't have enough data to be sure. With ATLAS, we have data, and it's contradictory. There's a pattern emerging across these 3 interstellar visitors. Each one has been different. Oumuamua was the inert tumbler, Borisov was the normal comet. ATLAS is the overachiever, doing too much with too little. If our sample size of 3 already shows this much diversity, what does that tell us about the interstellar object population as a whole? Are there categories we haven't even encountered yet? Do most visitors look normal and only a fraction show anomalies? Or is weird the norm and Borisov was the outlier? One possibility worth considering: maybe we're seeing a selection effect. Objects that are faint, inactive, or otherwise unremarkable might pass through our solar system regularly without detection. Our surveys are biased toward things that are bright, active, or close. Oumuamua was noticed partly because of its close pass by Earth. Borisov was bright with a visible tail. ATLAS is spectacularly active. For every one we detect, how many are we missing? If the answer is many, then our understanding of what's typical is fundamentally skewed. The comparison to Oumuamua also raises stakes for ATLAS. After Oumuamua, the scientific community promised itself it wouldn't be caught flat-footed again. Resources have been allocated, observation time secured, international cooperation arranged. December 19th represents a test of whether we've learned our lessons. Will we gather the data we need? Will we coordinate effectively? Will we be able to say definitively what ATLAS is, or will it leave us as puzzled as Oumuamua did? What's different this time is the level of public interest and the speed of information flow. Social media, instant communication, the 24-hour news cycle, all of these mean that ATLAS is being watched not just by astronomers, but by millions of people worldwide. That brings opportunities: crowdsourced analysis, distributed computing, fresh perspectives from outside the traditional academic structure. But it also brings challenges: misinformation, premature conclusions, conspiracy theories that spread faster than careful science can refute them. In the end, the comparison to Oumuamua and Borisov gives us context but not answers. We're still writing this story. On December 19th, we'll add a critical chapter, but the full narrative of interstellar visitors, what they are, where they come from, and what they mean for our understanding of the cosmos, remains to be written. Each visitor teaches us that the universe is stranger and more varied than we imagined. Whether it's also more populated, more technological, more alive in ways beyond simple chemistry and physics. That's the question ATLAS forces us to confront. Part 9, Controlled Event Models, If, Then. Let's play a thought experiment. Not because we know it's true, but because science sometimes requires exploring possibilities that feel uncomfortable. Suppose, just suppose, that 3I-ATLAS is not a comet in the sense we understand comets. Suppose it's something designed, built, launched, an artifact rather than a natural object. If that's the case, what would its behaviour tell us about purpose? First possibility: navigation. Interstellar space is vast, almost beyond comprehension. The nearest star to our Sun, Proxima Centauri, is 4.2 light-years away. That's 40 trillion kilometres, a distance so large that even travelling at 1% the speed of light would take over 4 centuries to cross. Any object making that journey would need to plan its trajectory carefully. You can't just aim at a star and hope you get close. Gravitational fields from other stars, interstellar matter, radiation pressure, all of these perturb your course over such distances. A close pass by a star, what's called a gravity assist or slingshot manoeuvre, is a standard technique in spacecraft navigation. You dive toward a massive object, pass close by, and steal some of its orbital momentum to accelerate yourself in a new direction. NASA does this routinely with interplanetary probes. Voyager used gravity assists at Jupiter and Saturn to reach the outer solar system. If 3I-ATLAS is using our Sun for a similar purpose, the perihelion pass on October 29th wasn't an accident, it was a planned manoeuvre. The jets we're observing could be course corrections, fine-tuning the trajectory coming out of that slingshot. Natural outgassing from a comet produces thrust, yes, but it's uncontrolled and relatively weak. Active propulsion, jets fired deliberately in specific directions, would allow precise targeting. If you're aiming for another star system and you want to arrive at a specific planet or region, you need that level of control. You can't afford to be off by even a fraction of a degree when your destination is light years away. Second possibility: observation. Our solar system is interesting. It has multiple planets, one with complex life, another with liquid water under ice shells, gas giants with intricate moon systems. If you're exploring the galaxy, cataloguing what's out there, this system would be worth a close look. A flyby trajectory gives you limited time but broad coverage. You can sample the solar wind, map magnetic fields, take spectroscopic measurements of planets, assess technological signatures from Earth. The perihelion pass would be the optimal point for certain measurements, especially those requiring proximity to the Sun or observations of the inner planets. The continued activity we're seeing, jets firing weeks after perihelion, could represent data transmission. If you've gathered information and need to send it back to wherever you came from, you'd need power, maybe lots of power, depending on the distance and bandwidth required. Directed energy beams, particle streams, these could look like jets to our instruments. We'd be seeing the exhaust of a transmitter operating at interstellar scales. Third possibility, energy harvesting. Stars are incredible power sources. Our sun outputs 3.8 times 10 to the 26th watts, continuously, reliably, for billions of years. If you're travelling between stars and you need to recharge, replenish fuel or gather raw materials, a close pass by a star makes sense. Maybe the jets aren't propulsion or outgassing at all. Maybe they're waste heat from power collection systems, or the exhaust from refining processes that extract useful materials from solar wind or magnetic fields. This sounds like pure science fiction, but the physics is sound. A sufficiently advanced civilization could build structures that harvest stellar energy, concepts like Dyson spheres or solar collectors on smaller scales. A probe passing through our system might deploy temporary collectors during perihelion, grab what it needs, and continue on. The jets could be coolant systems or manufacturing waste. Fourth possibility, signalling. What if 3I-ATLAS isn't here for us at all but is part of a network? Imagine a galaxy filled with objects like this, travelling between stars, creating a communication or navigation grid. Each one marks a point in space, transmits data, serves as a waypoint for others. The jets could be directional signals, beacons pointing toward other nodes in the network. We'd be seeing a message we're not equipped to understand, like watching someone use a semaphore flag system when you don't know the code. Now let's address the elephant in the room. If 3I-ATLAS is artificial, where are its makers? Why no direct contact, no clear attempt at communication with us? There are several possible answers, none of them fully satisfying but all logically coherent. Maybe we're not interesting enough. Our radio signals have only been propagating into space for about a century, a tiny bubble in galactic terms. Most of the galaxy doesn't know we exist yet. An automated probe following preset instructions wouldn't necessarily check for technological civilizations, especially if we only recently became detectable. Maybe the probe is ancient, launched thousands or millions of years ago, long before Earth had intelligent life. It's following its programmed route, doing its job, completely oblivious to the fact that one of the planets it's passing now has beings wondering about it. We're like ants discovering a discarded human tool, aware something artificial exists, but unable to communicate with whoever made it. Maybe direct contact violates protocol, some kind of non-interference principle. Science fiction loves this idea, the prime directive from Star Trek and similar concepts. If there's a galactic civilization out there, maybe they have rules about contacting younger civilizations. Automated probes can observe, but they're not authorized to make contact. We get scanned but not engaged. Or maybe the probe is defunct, a relic from a civilization that's gone. It's still following its last instructions, still powered by systems that run on physics rather than maintenance, but there's no one left to receive its data or issue new commands. We're seeing a ghost, technology, outliving its creators. The philosophical implications spiral outward from any of these scenarios. If interstellar probes are common, if they're out there in the galaxy travelling between stars, watching, mapping, transmitting, then the universe is a very different place than we thought. It's not empty space punctuated by isolated islands of life and intelligence. It's connected, networked, perhaps constantly monitored. The Fermi paradox, the question of why we don't see evidence of alien civilizations, gets reframed. Maybe we do see evidence. We just don't recognise it. Maybe it looks like weird comets with anomalous jets. But let's pull back from the brink here. Everything in this section has been conditional. If it's artificial, then maybe it's doing X. We don't know it's artificial. The default assumption remains natural object, unusual comet, extreme but explicable behaviour. Science requires evidence, not speculation. What December 19th can do is narrow the possibilities. If Atlas is fragmented, If we see clear signs of structural failure, the artificial hypothesis becomes much weaker. If it's intact and still active, the hypothesis stays on the table, neither proven nor disproven, but worthy of continued investigation. The question of purpose matters even if the answer is it's just a comet. Understanding why natural objects behave the way they do, what processes create these enormous jets, what compositions allow this level of activity, these are valuable scientific questions regardless of the origin. But if, in answering those questions, we find that natural processes genuinely can't explain what we're seeing, then we have to be prepared for what comes next. We have to be ready to say, this is technology, and mean it, with all the implications that carries. 10 days to December 19th. 10 days until we know whether to file 3I-ATLAS under astrophysics or astrobiology. 10 days until the universe either confirms our current understanding or shatters it. Sleep well. Part 10. Breakup models. How many pieces and how bad? Comets don't die quietly. When a comet fragments, it's rarely a clean split into two equal pieces. It's more like an explosion in slow motion, a catastrophic structural failure that sends debris flying in all directions at various velocities. We've seen this happen before, most famously with comet Shoemaker-Levy 9 in 1994, which broke into more than 20 distinct pieces before plunging into Jupiter. Each fragment followed its own slightly different trajectory, spread across hundreds of thousands of kilometers, creating a train of impacts that lasted for days. If 3I-ATLAS has broken up, we need to understand what that looks like mathematically and physically. Avi-Loeb's analysis provides a starting point. If the object has lost 16% of its original mass, which is consistent with the observed activity levels, then fragmentation would produce a minimum of 16 significant pieces, assuming roughly equal distribution. In reality, fragmentation is messier. You'd likely get a few large chunks, tens or hundreds of medium-sized pieces, and countless smaller fragments down to dust particle size. The surface-to-mass ratio is critical here. When a comet breaks apart, you're creating more surface area relative to total mass. A sphere has the minimum surface area for a given volume. Break that sphere into pieces and the total surface area increases dramatically. More surface means more area exposed to sunlight, which means more heating and more sublimation. For icy objects, this triggers a runaway process. Fragmentation leads to faster mass loss, which leads to further fragmentation, which leads to even faster mass loss. This is why comet breakups can be so spectacular. It's not just that the object splits, it's that splitting accelerates its destruction. Each fragment becomes a mini-comet, outgassing and potentially breaking up further. What starts as one object can become a diffuse cloud of thousands of pieces within weeks or months. The dust and small particles get pushed around by solar radiation pressure, spreading out along the orbit. Larger fragments follow trajectories close to the original path, but with slight deviations based on when and how they separated. For 3I-ATLAS, if breakup occurred around perihelion on October 29th, we're now about 6 weeks out. Computer simulations of cometary fragmentation suggest that debris would have spread across a region hundreds of thousands to millions of kilometers in size by now. The distribution wouldn't be uniform. There'd be clumps where larger fragments cluster, and trails of dust following the general orbital path. From Earth, this might appear as an extended, irregular coma without a clear nucleus, or as multiple distinct bright spots if the fragments are large enough and separated enough to resolve individually. The observational signatures we'd expect from breakup are specific. First, brightness fluctuations that don't correlate with distance. As fragments tumble and different surfaces face our direction, the reflected light changes unpredictably. Second, spectroscopic variation across the coma. Different fragments might be outgassing different materials based on their composition and structure. Third, trajectory spreading. Precise astrometry over multiple nights should show that the centre of light, the effective position of the system, is drifting in ways that pure gravitational motion doesn't explain. But here's where it gets concerning for satellite operators and mission planners. That debris doesn't just sit there, it's in motion, high-velocity motion, and it's interacting with forces that can change its trajectory significantly. Solar radiation pressure acts differently on different-sized particles. Something the size of a grain of sand can be pushed much more strongly relative to its mass than something the size of a boulder. Over time, this causes the debris field to expand and evolve in complex ways. The solar wind adds another layer of complexity. Freshly exposed ice sublimates and can carry away charged dust particles. These particles then interact with the solar wind's magnetic fields, potentially being deflected in unexpected directions. There's also the possibility of electrostatic effects. Dust grains can become electrically charged through UV radiation and particle impacts. Charged grains repel each other, causing the cloud to expand faster than neutral particles would. For spacecraft navigation, this creates a micrometeoroid hazard. Individual particles, even small ones, travelling at tens of kilometres per second relative to a spacecraft, hit with tremendous energy. A particle the size of a pea can puncture a satellite's hull or damage solar panels. A particle the size of a marble can destroy a spacecraft completely. The risk from any single particle is small, space is huge, and things are spread out. But if there are billions of particles scattered across a region that we regularly send missions through, the cumulative risk adds up. There's also the issue of debris tracking. NASA and other space agencies maintain catalogues of known objects in near-Earth space, tracking everything from active satellites to spent rocket stages to fragments from collisions. This tracking allows collision avoidance, manoeuvring spacecraft out of the way when orbits are predicted to intersect. But tracking only works if you know where things are. A diffuse debris cloud from 3I-ATLAS, especially the smaller fragments that are hard to detect individually, might not be fully catalogued for months or years. During that time, missions crossing the affected region would be flying semi-blind, aware of the general hazard but unable to pinpoint specific threats. Then there's the geomagnetic concern, which sounds exotic but is based on real physics. Earth's magnetosphere, our magnetic field's interaction region with the solar wind, is constantly fluctuating. Usually these fluctuations are driven by solar activity, coronal mass ejections and solar flares. But a dense cloud of charged particles from a different source, like cometary debris, arriving at high velocity could temporarily distort the magnetosphere in ways we haven't observed before. The effects would likely be subtle, unless the particle density and charge were very high. We might see unusual aurora patterns, radio communication disruptions in polar regions, maybe minor fluctuations in satellite electronics. The worst-case scenario involves significant electrical currents induced in power grids or satellite systems, similar to what happens during severe geomagnetic storms. Again, this is low probability, but the consequences could be significant, and we don't have much historical data to estimate risk accurately. The timeline for understanding the debris field extends well beyond December 19th. Even if observations on that date clearly show fragmentation, we'd only be seeing the large pieces and the general structure. Tracking individual fragments, characterizing the size distribution, predicting where the debris will be in weeks and months and years, all of that requires sustained observation campaigns. We're talking about international coordination, multiple telescopes, radar tracking from ground-based systems, maybe even spacecraft sent to image the debris field up close. This is one of the frustrating aspects of astronomy sometimes. Space moves slowly from our perspective. Things take time to evolve, to separate, to reveal their nature. We're accustomed to instant information, immediate answers, but 3I-ATLAS operates on its own schedule, not ours. We get glimpses, snapshots, pieces of the puzzle. Assembling the complete picture requires patience, coordination, and acceptance that some questions won't be answered for months or years. So if December 19th reveals a debris field, we'll know that 3I-ATLAS broke apart. That's valuable information. It rules out certain scenarios and points toward natural processes, overwhelming structural limits. But it also opens a new set of questions. How many pieces? How big? Where are they going? What risk do they pose? Those questions will occupy researchers long after the date passes, long after public interest moves on to other topics. The universe doesn't care about our attention spans. It unfolds according to physics, not news cycles. And physics says a fragmenting comet creates complexity that persists for years. Part 11. Quantum Gravity Telescope Proposal. While we've been focused on 3I-ATLAS, the broader astronomical community has been quietly working on the next generation of observation technology. In 2025, several research groups published proposals for what they're calling quantum gravity telescopes, space-based interferometry arrays designed to image the photon rings around black holes with unprecedented resolution. These instruments would test fundamental physics at the smallest scales, probing structure below the Planck length, and potentially revealing effects of quantum gravity. It sounds abstract, disconnected from our immediate concerns about comets and interstellar visitors. But the connection is more direct than you might think. The proposed telescope design involves multiple spacecraft flying in formation across baselines of thousands or even millions of kilometres. By combining the light received at each spacecraft using interferometry, the array would effectively create a telescope with an aperture as large as the separation between spacecraft. This technique, called very long baseline interferometry, isn't new. Radio astronomers have used it for decades, linking telescopes across continents to achieve incredible resolution. The Event Horizon Telescope, which produced the first image of a black hole's event horizon in 2019, used this approach with radio dishes around the world. What's new is extending the technique to shorter wavelengths and larger baselines. The quantum gravity telescopes would operate in optical and ultraviolet light, where wavelengths are much smaller than radio, allowing finer resolution. And by placing the array in space, free from atmospheric distortion and with the ability to position spacecraft precisely, the resolving power would exceed anything currently possible. Why does this matter for objects like 3I-ATLAS? Because the same technology that can image photon rings around black holes can also resolve small, distant objects with extraordinary detail. If a similar interferometry array were pointed at an interstellar visitor passing through our solar system, we could potentially see surface features, structural details, things that current telescopes render as mere points of light or blurry smudges. We could distinguish between natural and artificial with much higher confidence. Imagine if we'd had this technology when 1I/Oumuamua visited. Instead of guessing about its shape based on brightness variations, we could have actually seen its shape. We'd know whether it was elongated, flat, irregular. We might have detected surface features, craters, or smooth manufactured surfaces. The speculation could have been replaced with data. The same applies to 3I-ATLAS. Right now, even Hubble Space Telescope images show it as a diffuse glow with possibly a nucleus at the centre. Details about structure, rotation, surface composition, these come from indirect measurements and modelling. A quantum gravity telescope array, if it existed and were pointed at Atlas, could resolve the nucleus directly. We'd see what it actually looks like, not what we infer it looks like. The technical challenges are immense. Keeping multiple spacecraft in precise formation across vast distances requires incredibly accurate position control and timing. The light from each spacecraft must be combined with nanometer-level precision, accounting for the exact path length from the target to each collector. The data processing demands are staggering, correlating signals from multiple sources to extract coherent images. But these are engineering challenges, not fundamental physics limitations. The proposals published in 2025 include realistic mission architectures, spacecraft designs, budget estimates. The European Space Agency and NASA have both expressed interest in collaborative development. Funding hasn't been approved yet. These things take time, but the trajectory is clear. Within 10 to 20 years, we could have operational systems capable of this level of observation. There's an interesting parallel to draw here. The development of these advanced instruments is being driven by fundamental physics questions, understanding quantum gravity, mapping black hole structure, testing general relativity in extreme conditions. But once the instruments exist, they become tools for all of astronomy. Just as Hubble was built partly for cosmology, but has contributed to every field from planetary science to exoplanet detection, quantum gravity telescopes would be versatile resources. This is how scientific infrastructure advances. You build for one purpose and discover unexpected applications. GPS satellites were designed for navigation, but now contribute to earthquake detection, climate monitoring, even fundamental physics tests. The internet was created for military and research communication and transformed human society. A telescope built to study black holes could end up being humanity's tool for confirming or refuting the existence of interstellar probes. The timing is ironic. 3I-ATLAS is here now, forcing us to make judgments with limited data. The instruments that could definitively answer our questions won't exist for years. By the time quantum gravity telescopes are operational, Atlas will be long gone, continuing its journey through the galaxy, beyond our ability to track. If another interstellar visitor arrives in, say, 2035, we'll be ready. But preparation doesn't help with present mysteries. This pattern repeats throughout history. We develop better tools, then retrospectively wish we'd had them earlier. When Galileo first turned a telescope to the sky in 1609, he saw mountains on the moon, moons orbiting Jupiter, phases of Venus. Each observation overthrew centuries of assumptions. But he also saw things he couldn't understand, features that only made sense decades or centuries later with better instruments. The human timeline of understanding doesn't always align with the cosmic timeline of events. The quantum gravity telescope proposals also highlight something else: international cooperation in science. The mission architectures being discussed involve partnerships between European, American, Japanese, and other space agencies. This makes sense economically. No single nation wants to bear the full cost of such ambitious projects. But it also reflects a growing recognition that some questions are bigger than national interests. Understanding fundamental physics, detecting and characterizing interstellar objects, these are human endeavours, not national ones. There's a practical consideration as well. If we're going to build instruments capable of detecting artificial objects in space, objects that might represent technology from other civilizations, who should control those instruments? Who decides what gets observed, what data gets released, how findings are interpreted and communicated? These questions don't have easy answers. The scientific community values openness and peer review, but governments have legitimate security concerns. The tension between transparency and secrecy will only intensify as our detection capabilities improve. For now, the Quantum Gravity Telescope remains a proposal, a collection of papers and presentations and preliminary designs. But proposals become missions, missions become operational systems, and operational systems change what's possible. 3I-ATLAS is teaching us that we're not ready, that our current instruments leave too much ambiguity, too much room for speculation. The next generation of tools is being designed partly in response to that lesson. When the next visitor arrives, we'll do better. We'll have to, because the questions won't get easier and the stakes won't get lower. Part 12. The 2025 Lagrange Halo Swarm Concept. Detection is half the battle. Actually, it's more than half. You can't study what you don't know exists. This seems obvious, but it's worth emphasizing because of how it shapes our understanding of interstellar visitors. We've now confirmed 3 objects from outside our solar system: 1I/Oumuamua, 2I/Borisov, and 3I-ATLAS. 3 objects in 8 years. Is that the true rate of visitation, or are we missing most of them? The answer is almost certainly the latter. Our detection surveys are biased toward objects that are bright, large, or unusually active. Faint objects, small objects, or inactive objects that don't develop visible comae can pass through the inner solar system unnoticed. Computer models of interstellar object populations suggest the actual rate might be 1 or more per year, not 1 every few years. We're seeing perhaps 10 to 30% of what's out there. This detection gap motivated a concept that's been gaining traction in 2025, the Lagrange Halo Swarm. The idea is to place a network of autonomous telescopes in stable orbits around the Sun-Earth Lagrange points, specifically L1 and L2, the points where Earth's and Sun's gravity balance in ways that allow objects to maintain relatively fixed positions with minimal fuel expenditure. From these vantage points, telescopes would have continuous views of deep space, unobstructed by Earth or Moon, with stable thermal environments perfect for sensitive infrared detection. The key word is autonomous. These wouldn't be traditional space telescopes requiring constant human oversight. They'd run on artificial intelligence systems trained to recognize anomalies, patterns that don't fit known asteroids or comets. When something interesting appears, a new object on an unusual trajectory or an object showing unexpected behavior, the system would automatically alert human operators and redirect resources for follow-up observations. Think of it as an early warning network for interstellar visitors and other solar system oddities. The relevance to 3I-ATLAS is direct. If this swarm had been operational, we would have detected Atlas months earlier than we did, possibly even before it entered the inner solar system. That extended observation baseline would have given us data on its activity at greater distances, when it was colder and less active. We could have watched it turn on as it approached the Sun, seeing exactly when jets began to form and how they evolved. Instead, We only caught ATLAS when it was already relatively close and active. Early detection translates to better science in multiple ways. More time means more observations from different angles and wavelengths. It means coordination between space-based and ground-based telescopes can be planned rather than scrambled. It means spacecraft missions, if deemed worthwhile, could be launched with reasonable transit times to intercept the visitor while it's still in the inner solar system. Right now, by the time we fully characterize an interstellar object, it's usually already leaving, receding into the darkness where only our most powerful instruments can track it. The Lagrange halo swarm concept addresses this timing problem. Telescopes at L1, positioned between Earth and Sun, would have ideal views for detecting objects approaching from most directions. Telescopes at L2, on the far side of Earth from the Sun, would cover the opposite hemisphere and operate in the cold shadow of Earth's sunshield, perfect for infrared sensitivity. Together, the swarm would provide nearly complete sky coverage with overlapping fields of view, ensuring that few objects could slip through unnoticed. The AI component is crucial because of data volume. A network of dozens of telescopes, each imaging continuously, generates enormous amounts of data. Humans can't review it all in real time, but machine learning systems trained on known object databases, asteroids, comets, satellites, can flag anything that doesn't match expected patterns. The false positive rate would need to be low enough that operators aren't overwhelmed by alerts, but high enough that genuinely novel objects don't get filtered out. Striking that balance is a major technical challenge. Development status as of 2025 puts the swarm in the concept study phase. The European Space Agency and Japan's JAXA have both funded preliminary engineering studies. Cost estimates are in the billions, not cheap but comparable to other flagship space science missions. The timeline, if approved, would be roughly 10 years from funding to first operational capability. That means a decision in 2026 or 2027 could lead to deployment in the mid-2030s. There's debate within the astronomy community about priorities. Some argue that hunting for interstellar objects is interesting, but shouldn't compete with other pressing science goals like exoplanet characterization, dark energy studies, or near-Earth asteroid tracking. Resources are finite, and every mission funded means other missions delayed or cancelled. The counter-argument is that interstellar objects represent our only direct samples of material from other stellar systems. We can observe exoplanets with telescopes, but we can't touch them or analyse their composition in detail. An interstellar visitor passing through our system is a gift, a piece of the galaxy delivered to our doorstep. Missing it because we weren't looking would be scientifically irresponsible. 3I-ATLAS makes that argument more compelling. If this object turns out to be artificial, or even if it's just a natural object with properties we've never seen before, the case for dedicated detection infrastructure becomes overwhelming. Future congresses and parliaments considering funding for the swarm will point to ATLAS and ask, what if we'd had this system already? What might we have learned that we're now missing? Those questions will shape allocation decisions. There's also a security dimension that's rarely discussed publicly, but is part of closed-door conversations. If interstellar objects can be artificial, if there's even a small possibility of probes or other technology entering our solar system, then detection isn't just a scientific issue, it's a strategic one. Nations that can detect and characterize unknown objects have an advantage, whether that advantage is scientific prestige, technological insight, or simple awareness. No government wants to be blind to potential visitors, natural or otherwise. This creates a tension between the scientific ideal of open data and the security tendency toward classification. The Lagrange halo swarm proposals emphasize international collaboration and data sharing, following models like the International Space Station or the Event Horizon Telescope collaboration. But they also include provisions for rapid notification of national authorities if certain criteria are met, criteria that aren't publicly specified, but presumably relate to trajectory toward Earth or unusual characteristics suggesting non-natural origin. The parallel to 3I-ATLAS is clear. When astronomers first realized ATLAS was unusual, was there hesitation about publishing? Were government agencies briefed before public announcements? We don't know, and probably won't unless someone leaks documents years from now. What we can observe is that data release has been slower and more controlled than with typical comets. Whether that's caution, bureaucracy, or genuine concern about implications, the effect is the same. Public knowledge lags behind professional knowledge, sometimes by weeks. A properly functioning detection network would include protocols for this, clear guidelines on what gets announced when and to whom. The scientific community generally favours rapid release. The security community favours assessment first. Reconciling these positions requires compromise and trust, both of which are in short supply in today's geopolitical environment. 3I-ATLAS, regardless of what it ultimately proves to be, is exposing these fault lines and forcing conversations that should have happened years ago. In 10 days, on December 19th, we'll see how much our current capabilities can tell us. We'll also see the gaps, the questions we can't answer with existing infrastructure. Those gaps will define the next decade of space observation missions. The Lagrange halo swarm is one response. There will be others. The universe has shown us we're not seeing everything that passes through. Now we have to decide whether we're content with partial blindness or willing to invest in better vision. Part 13. Pulsar Timing AI Breakthrough. Pulsars are some of the most precise timepieces in the universe. These rapidly rotating neutron stars emit beams of radio waves that sweep past Earth like lighthouse beams, producing pulses with extraordinary regularity. The most stable pulsars, millisecond pulsars that rotate hundreds of times per second, tick with a consistency that rivals our best atomic clocks. Over years of observation, astronomers can predict when each pulse will arrive to within microseconds. Any deviation from that prediction tells us something happened to perturb the signal. What could cause such perturbations? Gravitational waves, ripples in space-time from colliding black holes or neutron stars, stretch and compress the space between pulsars and Earth, changing the arrival time of pulses by tiny amounts. This is how pulsar timing arrays work. They're essentially using the galaxy as a gravitational wave detector, with pulsars serving as reference points and Earth as the sensor. Over the past decade, these arrays have detected the background rumble of gravitational waves from supermassive black hole mergers throughout cosmic history. But gravitational waves aren't the only thing that can affect pulsar timing. Any massive object passing between us and a pulsar will create a gravitational perturbation, bending space-time slightly and changing the pulse arrival times. This is how astronomers have used pulsars to detect planets around other pulsars and to probe the distribution of mass in our galaxy. The precision is incredible. We can potentially detect masses as small as Earth passing through specific lines of sight if we monitor enough pulsars with sufficient accuracy. In 2025, a breakthrough in artificial intelligence applied to pulsar timing data processing has pushed that precision even further. Researchers developed neural networks that can model and subtract multiple sources of timing noise simultaneously, things like interstellar plasma variations, pulsar spin irregularities, instrumental effects. The result is timing residuals, the differences between predicted and observed pulse arrival times, with uncertainties at the femtosecond level. That's 10 to the minus 15 seconds. At this precision, we're approaching the ability to detect individual asteroid mass objects if they happen to cross the line of sight to a monitored pulsar. Now connect this to 3I-ATLAS. If this object, or others like it, has significant mass and happens to pass along or near one of the thousands of lines of sight to pulsars we monitor, there should be a detectable gravitational signature. The timing perturbation would be brief, lasting days to weeks as the object traversed the sightline but distinctive. By monitoring multiple pulsars and triangulating the timing anomalies, we could potentially determine the object's mass, trajectory, and velocity independently of optical observations. This is extraordinarily valuable because it provides orthogonal data. Optical astronomy tells us about light, brightness, colour, spectral composition. Gravitational effects tell us about mass, the actual amount of matter present regardless of how visible it is. For 3I-ATLAS, if pulsar timing data shows a mass consistent with the size we observe optically, that supports natural explanations. If the mass is significantly different, either much larger or much smaller than expected, that's a red flag demanding explanation. The practical challenge is coverage. There are about 3,000 known pulsars, and we monitor a few dozen very precisely for gravitational wave detection. The sky is vast, and the probability that any given object's trajectory crosses a monitored sightline is low. For 3I-ATLAS specifically, post-analysis searches through pulsar timing archives might reveal whether it passed near any monitored pulsars during its approach. If so, and if the data quality is sufficient, we'd have an independent mass estimate. If not, we'd have an upper limit. The mass couldn't have been above a certain threshold, or we would have seen a signal. Future implementations of this technique could be more systematic. If we monitor more pulsars, thousands rather than dozens, the network of sightlines becomes dense enough that most objects passing through the inner solar system would cross at least one. Combined with optical detection networks like the proposed Lagrange halo swarm, you'd have a multimodal detection system. Light tells you where and what, gravity tells you how much mass. Together, they provide a comprehensive picture. There's also an intriguing possibility for detecting stealth objects, things that don't emit or reflect much light but have significant mass. A dark interstellar asteroid, perhaps made of carbon-rich material with extremely low albedo, might be nearly invisible optically, but its gravitational effect on pulsar timing would be the same as a bright object of equal mass. This could help answer questions about the dark comet hypothesis and how many visitors we're missing because they don't light up when they approach the Sun. The 2025 AI breakthrough specifically addressed one of the major limitations in pulsar timing: noise mitigation. Interstellar space isn't empty. There's ionized gas, plasma, that the pulsar signals travel through. This plasma disperses the signal, affecting different frequencies differently and creating timing variations that obscure gravitational effects. Previous analysis methods could model simple plasma structures, but the galaxy is messy. There are filaments, clouds, turbulence, all creating complex dispersion patterns. Machine learning approaches don't try to physically model every plasma structure. Instead, they learn patterns from the data itself, identifying correlations between timing variations across different pulsars and frequencies. If multiple pulsars in the same region of sky show similar timing anomalies, that's probably a plasma structure affecting all of them. If a single pulsar shows an isolated anomaly, that might be a gravitational perturbation from a passing object. The AI learns to distinguish these patterns with much higher accuracy than traditional methods. The dual-use nature of this technology is worth noting. It's being developed primarily for fundamental physics, detecting gravitational waves, testing general relativity, probing dark matter distribution. But it's equally applicable to solar system object detection. This is common in astronomy. Techniques developed for one purpose become tools for entirely different applications. CCDs were developed for physics experiments and transformed digital photography. Adaptive optics were developed for astronomical imaging and now enable laser eye surgery. The AI timing analysis tools emerging in 2025 will find applications we haven't imagined yet. For 3I-ATLAS, the immediate application is retrospective. Can we search archival pulsar timing data from the past 6 months and find evidence of the object's passage? If the data exists and is sensitive enough, the answer might be yes. That would give us an independent check on mass estimates derived from optical observations and outgassing models. If the gravitational mass matches predictions, that supports natural composition. If there's a discrepancy, we have a puzzle to solve. Looking forward, integrating pulsar timing into routine solar system monitoring makes sense. It's not a replacement for optical surveys. You still need to see objects to track them precisely and study their composition. But it's a complementary layer, adding information that light alone can't provide. And for the specific question of whether interstellar visitors might sometimes be artificial, mass determination is crucial. A natural comet's mass should correlate tightly with its volume and assumed density. An artificial object might have very different mass-to-volume ratios, either much denser if it's made of metals and advanced materials, or much less dense if it's mostly hollow structure. The universe is constantly revealing new ways to observe itself. Every advance in instrumentation or analysis opens doors we didn't know were closed. Pulsar timing started as an exotic curiosity in the 1960s, pulsating radio sources that turned out to be neutron stars. Now it's a tool for detecting gravitational waves, mapping our galaxy's mass distribution, and potentially identifying anomalous objects passing through our solar system. 3I-ATLAS might benefit from this tool or it might not, depending on geometry and data quality. But future visitors certainly will. We're building a web of observation methods that will make the galaxy increasingly transparent. Anything moving through it, natural or artificial, will leave traces we can detect if we know where and how to look. Part 14. Superconducting Plasma Loop Engine Patent Race. Patents are interesting documents. They represent the boundary between theoretical possibility and practical engineering. Ideas developed enough that someone believes they might work and wants to claim ownership of the design. In 2025, several universities and private companies have filed patents for what they call closed-loop superconducting plasma engines, propulsion systems that use magnetically confined plasma and superconducting coils to generate thrust for long-duration spaceflight. The physics is complex, but the principle is understandable. Take a plasma, an ionized gas where atoms have been stripped of electrons. Confine it using magnetic fields, which can exert force on charged particles. Heat the plasma using electrical energy, microwave radiation, or other methods to increase its temperature and therefore pressure. Then release it directionally through a magnetic nozzle, and the reaction mass shooting out one end pushes your spacecraft the other direction. Basic rocket equation, but using electromagnetic forces instead of combustion. What makes these engines interesting is their potential efficiency and exhaust velocity. Chemical rockets are limited by the energy density of chemical bonds, a few electron volts per atom. This translates to exhaust velocities around 3 to 5 kilometers per second. Ion drives, which accelerate individual ions using electric fields, can achieve 30 to 50 kilometers per second. Plasma engines with optimized magnetic confinement and heating might reach similar or higher velocities, depending on design specifics and available power. Now remember the numbers from 3I-ATLAS. Typical comet outgassing produces velocities around 400 meters per second, less than half a kilometer per second. To maintain jets over millions of kilometers against solar wind pressure requires velocities substantially higher. Loeb's analysis suggests 10 to 50 kilometers per second would be necessary. That's precisely the range where advanced plasma engines operate. The patent applications filed in 2025 describe systems designed for human spacecraft, missions to Mars or the outer solar system, where high efficiency is critical. But the specifications could theoretically scale to much larger or smaller systems. If you were designing a probe for interstellar travel, a probe that needed to last thousands of years and perform maneuvers in multiple star systems, a superconducting plasma engine has advantages. Superconductors, once cooled, maintain current flow with no energy loss, meaning the magnetic confinement system could operate indefinitely, with minimal power input. Plasma can be generated from almost any material. You're not dependent on specific chemical propellants, as long as you have something to ionize and energy to accelerate it. The parallel to Atlas's jets is speculative but thought-provoking. If we observed a spacecraft using a plasma engine maneuvering near the Sun, what would it look like? You'd see directed streams of particles, visible if they contain dust or molecules that scatter sunlight or emit their own light from excitation. These streams would be collimated by the magnetic nozzles, appearing as jets rather than diffuse clouds. They'd have velocities consistent with the observed extent of Atlas's jets, millions of kilometers sustained against opposing forces, and depending on what material was being ejected, the spectral signature might or might not match what we see from natural outgassing. I want to be careful here. The existence of human patents for plasma engines doesn't prove 3I-ATLAS is artificial. Engineers develop technologies for all sorts of reasons, mostly based on known physics and imagined applications. The fact that we can design something doesn't mean nature can't produce similar effects through different mechanisms, but it does establish that the observed behaviour falls within the realm of engineered possibilities. We have, on paper at least, propulsion systems that could replicate what we're seeing. The patent race itself is interesting from a sociological perspective. Multiple entities are competing to claim intellectual property rights to similar designs, which suggests there's perceived commercial or strategic value. Space industry analysts predict that advanced propulsion will be a key technology for deep space missions in the coming decades, both government and private. Companies like SpaceX, Blue Origin, and newer startups are all investing in propulsion research. Universities are spinning off startups to commercialize lab prototypes. This creates an environment where advanced propulsion concepts move from theory to engineering faster than in previous eras. In the 1960s, when we were designing Apollo, the cutting edge was chemical rockets and early ion drives. Today, the cutting edge includes plasma engines, nuclear thermal propulsion, solar sails, and theoretical concepts like fusion drives or antimatter catalysis. If you'd told an engineer in 1969 that by 2025 we'd have patents for superconducting plasma engines, they might have believed you. but they'd expect those engines to be operational by now. The timeline from concept to deployment has been slower than the optimistic predictions of the space age, but it's accelerating. Private investment, international competition, renewed government interest in space exploration, all of these are pushing propulsion development forward. Within another 20 years, some of these patented designs will likely fly. When they do, we'll have direct experience with the signatures, exhaust characteristics, performance limits. That experience will inform how we interpret anomalous objects like 3I-ATLAS. There's also an ethical and military dimension that can't be ignored. Advanced propulsion technology has dual-use applications. A system that can push a spacecraft efficiently can also adjust orbits of satellites, or, in less benign scenarios, serve as a weapon delivery system or anti-satellite tool. The patents being filed are public documents, but the deeper research behind them, especially work funded by defense departments, is often classified. This raises questions about disclosure. If military labs have developed and tested plasma engines more advanced than public patents suggest, would that information be shared with civilian astronomers trying to understand 3I-ATLAS? The official answer is always yes. Science is transparent. National security wouldn't interfere with astronomical research. The practical answer is more ambiguous. There are layers of classification, compartmentalization, and bureaucratic friction that can delay or prevent information transfer even when no explicit secrecy is intended. For our purposes, the key takeaway is that advanced propulsion using principles consistent with observed behavior of 3I-ATLAS exists at least on paper and in laboratory prototypes. Whether nature can produce similar effects, whether Atlas is employing such technology, these remain open questions. But we're no longer in the realm of pure speculation. The engineering is real, the physics is understood, and the applications are being actively developed. If someone or something wanted to build an interstellar probe using plasma propulsion, the technology pathway exists. That doesn't mean they did, it means they could. Part 15. Dark Comet Hypothesis and the 2025 S5452 candidate. In May of 2025, a team using the Subaru telescope in Hawaii announced the detection of an object they designated S5-452. The name is unremarkable, a catalogue identifier like thousands of others. What made S5-452 interesting was its albedo, the fraction of light it reflects. Most asteroids have albedos between 5 and 30%, reflecting a decent portion of the sunlight hitting them. Some comets, covered in dark organic compounds, can be as low as 3 or 4%. S5-452 measured less than 2%, making it one of the darkest natural objects ever observed. The orbit was equally curious. 5-452 moves in a nearly circular path around the Sun at roughly 1 AU, Earth's distance, but inclined significantly to the ecliptic plane. It's not on a collision course with Earth, but it's also not in a typical asteroid belt orbit. The dynamics suggest it might have been perturbed inward from farther out, or possibly captured from an unbound trajectory long ago. Detailed orbit determination is ongoing, but preliminary models can't rule out an originally hyperbolic trajectory that got circularized through interactions with planets. This brings us to the dark comet hypothesis, the idea that some objects in our solar system, and perhaps passing through it, are so dark, so non-reflective, that they escape detection despite being relatively large and nearby. We've known dark asteroids exist, objects made of carbonaceous material that absorb most incident light. But the hypothesis extends this to suggest there might be a population of extremely dark objects with albedos under 1% that we're systematically missing because our surveys rely on reflected sunlight. If you can't see it, you can't track it. If you can't track it, you don't know it's there. This is a detection bias that could be skewing our understanding of what's in the solar system and what visits from interstellar space. We assume we're seeing most of the large objects because we've surveyed most of the sky to reasonable depth. But reasonable depth assumes objects reflect a certain amount of light. If they don't, they're invisible to surveys calibrated for normal albedos. 3I-ATLAS, for all its oddities, is relatively bright because of its jets and coma. The gas and dust scatter sunlight effectively, making the object detectable from great distances. But what if some interstellar visitors don't develop coma? What if they're solid, non-volatile bodies that remain dark and inert as they pass through? They could be all around us, undetected, following trajectories we'd find very interesting if only we knew to look. S5-452 might be one of these stealth visitors. Its low albedo means it was only detected because it happened to pass close enough that even reflecting 2% of sunlight made it just barely visible to Subaru's sensitive instruments. If it were slightly smaller or farther away, we'd have missed it entirely. Multiply this by the volume of space and the number of potential objects, and you get an unsettling conclusion. Our inventory of solar system and interstellar objects might be radically incomplete. The connection to ATLAS is this. If there's a class of dark objects we're not detecting, then the interstellar visitor rate could be much higher than we think. We've confirmed 3 in 8 years, but that might represent only the tip of the distribution, the bright ones or active ones. There could be tens or hundreds passing through that we never see. They wouldn't threaten Earth. Space is too vast for random collisions. But they'd represent a massive blind spot in our awareness of galactic traffic. Why would objects be so dark? Natural explanations include composition, certain materials like magnetite or graphite are highly absorbing, and surface processing. Radiation and micrometeorite impacts over millions of years can create rough, porous surfaces that trap light rather than reflecting it. There's also the possibility of organic tholins, complex carbon-rich compounds that form from ultraviolet radiation on ices, which are among the darkest materials known. Less natural explanations involve deliberate design. If you wanted a probe to avoid detection while travelling through star systems, making it highly absorptive across visible wavelengths would be sensible. You'd lose some solar energy that could be harvested, but you'd gain stealth. Whether stealth is advantageous depends on the purpose. If you're observing without wanting to be observed, yes. If you're trying to communicate or establish presence, no. So the existence of dark objects tells us about intent, if they're artificial, but doesn't tell us what that intent is without more data. The Subaru team studying S5-452 is planning follow-up observations with infrared telescopes. All objects emit thermal radiation based on their temperature, and infrared detection doesn't depend on reflected light. If S5-452 is real and as dark as initial measurements suggest, infrared imaging should see it clearly and provide data on size, temperature, and thermal properties. This will help distinguish between natural ultra-dark material and potentially artificial surfaces with unusual emissivity. For the broader dark comet hypothesis, the way forward involves expanded surveys at multiple wavelengths. Visible light surveys will continue to miss the darkest objects, but combining optical, infrared, and potentially radar observations can fill gaps. Radar is particularly powerful because it doesn't depend on the object's reflectivity in visible light. You send out a signal and detect the echo. Even a perfectly black object scatters radar waves. NASA's planetary radar systems have detected and characterized numerous near-Earth objects this way, providing shapes and orbits for things that are optically faint. If 3I-ATLAS is part of a larger class that includes dark, inactive objects alongside bright, active ones, then our characterization of interstellar visitors is fundamentally incomplete. We're looking at a biased sample, the flashy ones, and missing the majority. It would be like trying to understand human civilization by only observing fireworks displays. You'd learn something, but you'd miss most of the picture. December 19th won't answer questions about dark objects directly. 3I-ATLAS is bright, active, unavoidable, but the context matters. If we determine ATLAS is natural but weird, we still have S5-452 and potentially other dark candidates raising separate questions. If we determine ATLAS might be artificial, the existence of a dark object population becomes immediately relevant. Are they related? Different categories of the same phenomenon? Completely separate mysteries? We don't know yet. What we can say is that 2025 has been a year of expanding mysteries in the field of solar system studies. Not answers, mysteries. That's not bad for science. Mysteries drive investigation, funding, collaboration. Answers are satisfying but terminal. They close doors. Mysteries open them. 3I-ATLAS and 5-452 are opening doors we didn't know existed, revealing gaps in our knowledge and biases in our methods. The universe is showing us where we're blind. Now we have to decide whether we're content with that blindness or committed to expanding our vision, whatever the cost and wherever the truth leads. 10 days remain until December 19th, 2025. 10 days until telescopes around the world and in space converge on a single point of light receding from the sun. What they see will shape decades of research, policy, maybe even philosophy. If 3I-ATLAS has fragmented, we'll learn about exotic comets and the limits of ice structures. If it remains intact, we'll face questions about propulsion, origin and purpose that science isn't fully prepared to answer. Either way, we're witnesses to something unprecedented. An interstellar visitor displaying behaviour that challenges our models, arriving at a moment when our observation technology is just barely adequate to study it, and our cultural conversation is just barely ready to consider implications beyond the purely natural. The timing might be coincidence, or it might be that we only notice what we're prepared to see, and 2025 is when humanity became prepared to ask whether we're alone in our making of tools and sending them between stars. Sleep if you can. The 19th approaches, and with it, the universe delivers its verdict on what we think we know.